Welcome back. So, have you got it figured out? Do you know what these combination counts come out to be? And again, this is just a simple number crunch using this formula, or just using kind of our logic where we find our permutations first and divide away redundancies. In any event, the first formula here, we've got 6 factorial over 2 factorial, 4 factorial. You then multiply all those things out, cancel out your common factors, and you are left with 15 ways. This means there are 15 different ways to choose 2 things out of 6 with order not mattering. Similarly, we've got 5 choose 3. So this will eventually reduce down to be 5, 4, 3 over 3, 2, 1, which is 10. There's 10 ways to pick 3 out of 5, assuming order doesn't matter. And then 10 choose 5, similar idea. I've given you some hints as to how you might work this out by hand if you need to here, right? I write 10 times 9 times 8 times 6 times 3, and that goes, this is basically the permutations part, right? If I am picking 5 out of 10 and order matters, I would count 10 times 9 times 8 times 7 times 6 ways. But then I would deal with the redundancies and divide away 5 factorial, 5, 4, 3, 2, 1. So what all this comes together to give me is, well, I do a little bit canceling here, right? The 10 and the 5 reduces to 2, and then the 8 and the 4 reduce to 2, and then, of course, 6 divided by 3 times 2 times 1 is 1, so all this comes out to be 252. So there are 252 different ways to pick 5 things out of 10. And then hilariously, 100 choose 100 as a permutations problem, that would be a thing of nightmares. But if order doesn't matter and you're picking everything, there's only one way you can pick everything, and that's by picking everything. Of course, if order does matter, it's going to be a big number. But if order doesn't matter, you go all the way down to 1. You just pick everything. And really, believe it or not, that's the entire gist of this section. What I'm going to do with the next couple of videos is just work some examples with you guys, just to get you acquainted with some of the application problems you might see if you're working on WebAssign or Pearson or what have you. And this is something that a lot of students know, but some students don't. So for whatever reason, actually I know the reason, it's because probability theory and gambling went hand in hand in its inception, and that still is kind of true today. But anyway, we want to talk about cards. So just to give you a heads up, a deck of playing cards has 52 cards on it. There's 4 suits, and diamonds, hearts, spades, and clubs are the 4 suits. And every suit, since it divides 52 evenly, is 13 cards. So there would be an ace of hearts, a 2 of hearts, a 3 of hearts, a 4 of hearts, a 5 of hearts, a 6, 7, 8, 9, 10 of hearts, as well as a jack of hearts, a queen of hearts, and a king of hearts. 13 cards altogether. That for every suit, 13, 13, 13, 13, comes out to be 52 cards. And I'm not going to get into poker theory with you. I'm not going to get into blackjack theory with you. But certain card combinations are advantageous depending on the game you're playing. So let's start with a very simple question. How many different ways could you draw the 4 aces out of a deck of 52 cards? And we'll do it twice. First, we'll assume order matters, and then we'll assume that order doesn't matter. So I've started listing out the ways, right? Let's assume we draw the ace of spades first. Then I could draw maybe the ace of clubs next, or the ace of diamonds next, or the ace of hearts next, one of those 3. And depending on which I draw first and second, then there's 2 left there for either diamonds or hearts or whatever. And then finally the 4th draw. So I have what? 1, 2, 3, 4, 5, 6. 6 combinations. I'm sorry, not combinations, right? Order matters here. 6 permutations, given that I drew the spades first. So you might be able to conclude there's 24 different combinations. But there's got to be a smarter way about this. So we will look at the smarter way in the next video. Maybe you can come up with it first. Either way, I'll see you then.